Hello, nice to have you here again. Today, let's learn about permutations, anagrams. It's going to be super fun. So, how many permutations do we have? What's a permutation anyway? A permutation is a rearrangement of a finite number of a number of objects. So, for instance, here I have a set S with the numbers 1, 2, 3. Very easy example, okay, to start. To warm up, and we have a bijection. A bijection is a function that maps each point here to a point here, and different points in my domain have to be mapped to different points of the codomain, and it has all points of the codomain have to be receiving exactly one arrow. Okay, so it has to be injective and surjective at the same time. So what would be a one way of doing this task? I could map, say, the number 1 to 3, the number 2 to 1, and the number 3 to 2. Okay? So f of 1 would be 3, then f of 2 would be 1, and finally f of 3 should be 2. That's just one example. I could have done differently. I could have mapped 1 to 1, 2 to 3, 3, lots of examples. So how many overall? So when I'm doing this, I have to do 3 tasks. I have to tell you, to precisely define the function, I have to tell you where 1 is going to be going, where 2 is going to be going, where 3 is going to be going. But it has to be a bijection, so I cannot send 2 different numbers to the same number here. Okay, so the first task I have to do, task number 1, is choose where 1 is going. And I have 3 options. I can map the number 1 to itself, to 2, or to 3. So here I have 3 different ways of choosing f of 1. However, after I chose whatever number I chose here that's occupied, cannot have other points going there. So when I have to map number 2 into a point of this set, one of the points is already unavailable, okay? So I have only 2 options to choose. And after I map number 1 to some point here, number 2 to some point here, for number 3, I have only one available option, only one available point. So I have one possibility to do this task. Okay, so by the multiplication principle, I have 3 times 2 times 1 ways of doing the whole thing. Okay, so I have, in this case, 3 factorial, 6 permutations of the set with 3 elements. In general, when we have a set with n elements, there will be n factorial permutations. For a set with exactly n elements, there will be n factorial different permutations of the set. Again, I have the first element, I have n possibilities, then the second n minus 1 possibilities, the third n minus 2 possibilities. I multiply everything using the multiplication principle again, and I have n factorial permutations of a set with n elements, okay? Now, come with me here. What about anagrams? So suppose we have this word car, and I have to switch the order of the letters. How many different words can I make? How many anagrams do I have? Well, I listed all 6 anagrams, because these are exactly the same problem of finding permutations of a set with 3 elements. If we have 3 letters, and the letters are all different between themselves, then I'll have 3 factorial equals 6 permutations. So I have 6 anagrams, and I list here the 6 anagrams, okay? The words that start with C, then the 2 words that start with an A, and the 2 words that start with an R. Overall, 6 anagrams of the word car. What if I have the word N? So in principle, I can put the A on the left, like in these two examples here. I can put the letter A in the middle, like in these two examples here, or I can put the A on the right-hand side as in these two examples here. So here I have only 3 anagrams. What's the difference? Why do I have 3 anagrams here and 6 here? Well, I think you can understand. I put an index here on the letter N's to pretend that the N's are different from each other. This is N1 and this is N index 2. Here I have N2 ahead of N on the left of N1, and here N2 is on the right of N1. But it's the same word, right? It's A N N. Because these indices are just pretending, right? They're not real indices. The word letters don't have indices. So, but what was the trick to count that in general? More in general, you pretend that the letters that are repeating are different letters, and then you have n factorial, you count the number of letters, and then you have to divide by how many permutations I have among the letter that is repeating. For instance, here I pretend that I have 3 different letters. I pretend that N1 is different from N2. And then this would be a word with 3 different letters. I would have 3 factorial permutations, but I'm counting too much. If I do that, I don't have 6 anagrams. I only have 3. Why? What's the problem here? Is that when I'm counting these 2 different words as 2 different, if I'm counting like this, but they're the same word, right? I don't have these indices. So I have to divide by 2 my counting. And then I will have 6 divided by 2, which is 3. I got the correct answer in the end, okay? Doing this trick. How about the word Anna with double N? I can write like this. So I will have 6. That is very suspicious, but you told us that you would do the trick. Yeah, we could do the trick. We could pretend that the N's are different and the A's are different. Okay? And if the 2 N's are different letters, if they were different letters, and the 2 A's were different letters, I would have 4 factorial anagrams. But we know that 4 factorial is 24, but we listed here only 6 anagrams. 24 is different from 6, so something is wrong if I'm doing this calculation, and you know what is wrong, right? Because if I switch N1 with N2, I have the same word. I have this word here. No matter if I have N1, N2, or N2, N1, I have the exact same word. So I'm doing some double counting here. On the ends, I'm also doing some double countings of the A's because I could switch the order here. So this single word here, I'm counting 4 times. 2 times by switching the N's and 2 times switching the A's. I could have N1, N2, A1, A2. I could have N1, N2, A2, A1. I could have N2, N1, A1, A2. And I could have N2, N1, A2, A1. So these 4 possibilities, they all lead to the same word, the word N, N, A, A. Okay? So I have to divide this 4 factorial by 4. And then I have 6. Okay? Which is this 6 here. The 6 possibilities. Okay? So every time I have a repeated letter, I have to divide by the factorial of this letter how many times I have repeated. Okay? For instance, here, let's think of the word banana. 1, 2, 3, 4, 5, 6 letters, so it's a 6 factorial. But I have repetition, so I'm counting too many A's. I have 3 A's, which I can permutate, and I have 2 letter N's, which I should be able to permutate as well. So how much is this? This is 6 times 5 times 4. I cancel with the 3 times 2. So here's 1, here's 2. 30 times 2. 60 anagrams of the word banana. Okay? How about the word book? I have 4 letters, 4 factorial, but I have 2 letter O's. So I have 12 anagrams of the word book. Okay? How about the word Mississippi? Whoa, a difficult one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial divided. The I's, I have 1, 2, 3, 4 letter I's. So 4 factorial. I have a 1, 2, 3, 4 letter S's. And I have 2 letter P's. Here and here I have P's. Do I have more repeated letters? No, right? I have only one M, so I don't have to put 1 factorial here. So yeah, I don't even want to do this calculation, it's going to be too big. How about the word Peter? There's another way you could that. You could think about, this is the first position. I have to put a letter here, a letter in the second position, in the third position, in the fourth position, in the fifth position. Okay? So what I could do is I have to put these 5 letters here in these 5 positions. Position number 1, 2, 3, 4, 5. So I have to choose where I'm going to put this letter E that is repeating. I could put the E here and here, or here and here, or here and here. Lots of possibilities. So basically I have to choose 2 out of the 5 positions to put the letter E. And I have exactly 5 choose 2 ways of doing that. After I put the letter E, say, for instance, I put the letter E here and here, I have to put the P, T, and R in the other 3 empty positions, and I can do that in 3 factorial ways. Okay? I can permutate the P, the T, and the R in the 3 empty spots, and I have this many ways of doing that. Okay? So this binomial symbol is this. The 3 factorial is here, and then I cancel. I have 5 factorial over 2 factorial, which is 60. Okay? So that's another way to do the problem. Okay? I hope you can see that this is exactly the same as before. If I just use what we learned before, I have 5 letters, and I'm repeating the E twice. So I could go directly to that if I know how to do it. Or I could do by choosing the positions of the E, as you prefer. Okay? But the idea is the idea of permutations. This idea is an extremely powerful concept in mathematics. Now, let's talk about equations. So suppose you have an equation x1 plus x2 plus x3 equals 4, and we have to count how many solutions this equation has, but each variable x1, x2, and x3 has to be an integer number, non-negative integer number. 0, 1, 2, 3, at most 4, right? So each xi has to be a non-negative integer. How many different solutions do I have for this equation? So here's the technique. Here's my trick. I'm gonna write the 4 as putting 4 objects here as these blue balls. And then I have to separate these blue balls in 3 categories. some of the balls will be in this basket, in this category, some in this, some in that. I will put divisors, separators, okay? So I can put two red separators like in this here, in these positions here after the balls, or like this, or like that, or in any way that I want between the balls, right? I can just put two separators to divide the 4 balls into 3 different groups or categories. Okay, the balls that are on the left-hand side of both separators, the balls that are on the right-hand side of both separators, and the balls that are in the middle. The number of balls on the left of both separators, that's going to be x1. The number of balls between the 2 separators, that's going to be x2. And the number of balls to the right-hand side of both separators are going to be x3. Okay? So then I can put any solution I can associate with this diagram here. For instance, x1 equals 4 means all 4 balls are to the left of both separators. Between the separators, there's 0 balls, x2 is 0, and to the right of both, I have 0, x3 is 0 in this solution for this diagram here. Here, to the left of both, I have 3 balls, so x1 equals 3. Between then, the 2 separators, the 2 divisors, I have a single ball, so x2 equals 1. And to the right of both, I have no ball, 0 ball, so x3 is 0. Here I have 1 ball to the left, x1 equals 1. 2 balls to the right, 2, and exactly 1 ball in the middle, x2 equals 2. So here I have 0 balls to the left, x1 equals 0. I have exactly 1 ball between the 2 separators, the 2 divisors, x2 equals 1. And I have 3 balls to the right, x3 equals 3. And I can continue doing that for all possible configurations. The important thing here, the thing you have to understand is here, each time I write this one diagram like this, I have one and only one solution. And more than that, for each possible solution, I can draw a diagram like that. So that gives me this idea of bijection, right? A bijection between the diagrams and the number and the solutions. So it turns out that when you have finite sets, if there are 2 sets, A and B, and there's a bijection between them, these 2 sets have to have the same number of elements. So this notation is the number of elements of set A equals the number of elements of set B. And it's a if and only if kind of result. If the 2 sets have the same number of elements, then there exists a bijection. Maybe not every function from A to B will be a bijection, but that at least there is a bijection. Okay? If the 2 sets have different numbers, so this is set A and set B. I have functions from A to B, but no bijection. It's impossible to make a bijection, right? These 2 points will have to go to the same point here, or if I have 3 points here and 2 points here, the pigeonhole principle tells me that they're gonna have to have multiple points going to the same point of A. Multiple points of my domain will be mapped to the same point. That's no bijection here, okay? Why do we have no bijection no matter how much you try? Because the number of elements of A is different than the number of elements of B. Okay, so there is a bijection if and only if the 2 sets have exactly the same number of elements. Okay, and here what's happening, so this gives us this powerful technique to counting number of elements. Suppose I can construct a bijection and I know how many elements my set B has. Well, that has to be the same, exact same number of elements that set A has. So that's the technique I'm using here. I don't know how many solutions I have, but I know how to build this bijection between solutions and these diagrams here. But these diagrams here, what is a diagram like this? This is an anagram of a word with 4 letter O's and 2 letter I's, right? Depending on where I put the I's and the balls and the separators, you can think of this divisor or separator as the letter I, and this object here as the letter O. And how many anagrams do I have? If I have 4 letter O's, 1, 2, 3, 4 O's, and 2 separators, 2 divisors, 2 letter I's. Well, overall we have 6 letters. I'm repeating 4 and 2. So 6 factorial, I cancel with the 4 factorial, I have 6 times 5 over 2. So that's 15. Okay. 30 over 2 is 15, or I cancel the 6 and the 2 and I have a 3 times 5, 15. So I have 15 anagrams of this word. Therefore, I will have 15 different solutions to my equation, where each xi is a non-negative integer number. Okay, that's the trick to calculate the number of integers, of solutions, non-negative integers for this equation. Very nice trick, beautiful trick. Now let's do a harder problem. Let's say we have the equation x1 plus x2 plus x3 plus x4 equals 15. So we have 15 objects we have to separate in 4 groups, and we want integer solutions, but the solutions have to start at 2. We have to have a minimum of 2 in each category, a minimum of 2 objects in each category. Okay, this xi can be 2, 3, 4, or any bigger number. They have to add up. x1 plus x2 plus x3 plus x4 have to add up to 15, but each xi has to be at least 2. Okay, so how do we do that? Well, we do something a bit obvious. We have to do a minimum of 2 for each category. So we give 2 objects to each category. How many objects have I used so far? 2 times 4 categories, 8. And I have 7 out of the 15. If I have used 8 objects, I have still 7 to distribute, but now I can distribute freely. Okay? So in formal terms, I make this new variable, the yi xi minus 2, right? So this, if xi is 2, my y is 0. If xi is 3, my y is 1, and so on and so forth. Okay? So I can push this negative 2 to the other side, so xi is yi plus 2. I take my original equation, instead of x1, I write y1 plus 2. So this is x1, this is x2, this is x3, this is x4. They have to add up to 15. So I have the sum of the y's plus 2, plus 2, plus 2, plus 2 equals 8, equals 15. Subtract 8 from both sides. I have the sum of y's are going to be 15 minus 8, or 7. And now this y, these variables y, they can be 0, 1, 2. I have freedom now. Okay? That's how I overcome this challenge of having at least 2. And now I can use my trick. Here I have 7 balls, so I have 7 blue balls, and I have to separate in 4 groups, so I have 3 separators, 3 divisors. I can put in any position. So for instance, here the solution would be y1 equals 1, y2 equals 2, y3 equals 4, and y4 equals 0. I have 0 blue balls to the right here, which would, when I add 2, this would correspond to x1 equals 3, x2 equals 4, x3 equals 6, x4 equals 2. 3 plus 4, 7, 13, 15. Okay, so this diagram here corresponds to this solution to the original problem. okay? And how many anagrams do I have with 6 letters, with 7 letters O, okay? So I have 7 O's, and I have 3 letter I's. How many anagrams do I have here? So I have a total of 10 letters. I'm repeating 7 O's and 3 I's. So canceling, I would have 10 times 9 times 8, divide by 3 times 2. So here's 3, here's 4, and I have 12 times 10, 120 solutions to this problem. Okay, so I have 120 solutions for this equation here, such that each solution is an integer number at least 2 or more in an integer number. Okay, and I have exactly 120 solutions for this. Very clever. One more exercise. Now, how about inequalities? If I have an inequality, x1 plus x2 plus x3 plus x4 plus x5 smaller or equal to 20. How many solutions do I have? I let each solution be an integer number, 0, 1, 2, non-negative integer, okay? So the trick to do this with inequalities is to look for the gap between this sum and 20 and call the gap another name, another variable. So the y measures my gap, okay, to 20. So it's 20 minus the sum that I have. If my sum is 0, this y is 20. If my sum is already 20, the y is 0. So the y will be an integer number between 0 and 20, perhaps 0, perhaps 20, perhaps something in between 20 and 0. Nevertheless, each solution of this inequality corresponds to one and only one solution of this equation here. Okay? That's the trick. So think about that deeply and convince yourself that each solution here of this inequality corresponds to one and only one solution of this equation, and each solution of this equation corresponds to one and only one solution of this inequality here. It's a one-to-one, so there's a bijection, so the number of solutions of this inequality is the same as the number of solutions of this equation here. But now this equation, we know how to do it, okay? The y can be 0 or also falls on this region. So I have the trick with anagrams. So I have here 1, 2, 3, 4, 5, 6 categories. I have 6 categories and I have to split 20 objects. So I have 20 balls and I have 6 categories. So how many separators to divide the 20 balls into 6 categories? I need 5 separators. Okay, so I have 20 and 5. And how many anagrams? Is 25 factorial over 20 factorial, 5 factorial. That's a big number. I'm not gonna solve it. Okay? How about if your inequality had a strict instead of smaller or equal, it would be this. Well, this problem is the same as x plus y plus z is smaller or equal to 7. Okay? If it has to be strictly smaller than 8, so the sum has to be at most 7, because these are integer numbers. Okay? And now I can think about the gap and can write the equation as, think about a gap as being 7 minus x minus y minus z, and I have the equation x plus y plus z plus the gap equals 7. So I have 7 balls, a group of 7 balls, 7 objects, and I have to separate in 4 categories, 4 groups. So I need 3 divisors. So I have how many solutions? I have 10 factorial over 7 factorial, 3 factorial solutions. Okay? So hope you enjoy. See you next time. Bye bye.